Hello everyone, we are starting a new chapter, chapter 6, sampling and sampling distributions. So in this chapter we will look at some basic inferential statistics like how we can get information about population using sample. So basically we are using the sample statistics to get information about population parameters. Now we do not know the population parameters, but we can use the sample statistics to have an idea, like an estimation about the population parameters. So normally in this chapter we will have sampling distribution of sample means, sample proportions, and sample variance. We will not see variance, we will only look at sampling distribution of sample means and sample proportions. So sample mean is something easy to calculate. We simply add up all the numbers in the sample and divide by the sample size. That will give us the sample mean. So it's basically the average of the sample observations. Now, the standard error of the sample mean is a bit different because different samples of same size from the same population will lead different sample means. So here the standard deviation of the sample mean, like sigma x bar, is equal to the actual standard deviation divided by the square root of n divided by the sample size. Now, there is a way to calculate this number, like this is actually based on some simple algebra, but for this course we are skipping the algebra, you just need to know the formula. So here we have an example. Now, let's say we have a population of 4 and mu is 21 and sigma is 2.236. Now we want to find the distribution of the sample mean, how the sample mean is distributed. So we take different samples from this population. Now the population might have different types of distributions, but at the end the mean of the sample is distributed almost like a normal curve, where you have the center and you have a standard deviation. So that's the idea of sampling distribution. So simply put, you put all the numbers, like how many numbers that you find, divide by the total size of the sample, and that will give you the mean. And for the variance of the sample mean, you do the same thing, like usual variance, but this time you divide by the sample size, and that will give you the variance of the sampling distribution. So if the population is normal, our job is very easy. The mean of the sample mean is the same as the population mean. The standard deviation of the sample mean equals the population standard deviation divided by the square root of n. Now there's a discussion when the sample size is not really large. We will skip that discussion. We will assume that our sample size is large enough. So we only need to use this formula here and this formula here. Now, the sampling distribution of the sample mean can also be standardized. Now, how do you standardize? You simply take x bar minus mu of x bar over sigma of x bar. Now, mu of x bar is the same thing as mu, but sigma of x bar is sigma over square root of n. So the sample distribution is also distributed normally with mean equals mu, standard deviation equals sigma over square root of n. And obviously the expected value of the sample mean is the mu. So both distributions, the population distribution and the sample distribution, have the same mean. What's the difference is the standard deviation. Now, the standard deviation of the sample mean equals sigma over square root of n. What that means is, as the sample size gets higher, the standard deviation of the sample mean gets lower. So for example, here, this is the population distribution with a higher variance, higher standard deviation, and this is the sample distribution with a lower variance and lower standard deviation. Now, the idea is, if you have a smaller sample size, you will have a larger standard deviation. If you have a larger sample size, you will have a smaller standard deviation. So basically, let's say n, okay, n is the sample size. If that number goes up, what happens is the standard deviation of the sample mean will go down. Why? Because this number is equal to sigma over square root of n. So there is an inverse relationship between the sample size and sample standard deviation. And this works even if the population is not normal. But for very small populations, this may not work. But for our course, we will use a population that is large enough. So what do we mean by large enough? Large enough means something like, as long as n is higher than or equal to, let's say, 30. But for this course, we will use our sample, and our sample is very large, actually, 106, 140. So that will be large enough. So the idea is, according to center limit theorem, if the sample size is large enough, we have a large sample size, then the standard normal distribution of the sample mean will approach the standard normal distribution. So it becomes like, standard normal distribution is 0 and 1. So mean 0, variance equals 1. So the idea is the mean of a large sample can be standardized. In that case, this will be distributed normally with mean equals 0 and variance equals 1. That's the idea. Well, the book said n is greater than 25. I said n is greater than 30. That number, doesn't make much difference for us because our sample size is large. Since it's large enough, our sample is, we can assume that it will be normally distributed. So here's an example. We have a large population with mu equals 8, sigma equals 3. And we choose the samples of 36. What's the probability that sample mean is between 7.8 and 8.2? So if we write this as like a notation, we are looking for the probability that 7.8 sample mean, that's x bar, is less than 7.8 and 8.2. So this is what we are looking for, and here's the answer. So the mean equals 8. Standard deviation equals the sigma over square root of n. So that probability here, the probability that the sample mean is between 7.8 and 8.2, can be converted into this notation. And at the end, we are looking for the probability that the sample size, the z-score, is between minus 0.4 and 0.4, and this will become 0.3108, and we get this number from the table. So the next one is the acceptance interval. You know, it's actually sometimes called the confidence interval, and those things that are something that we're going to use in our research project. So we are looking for, in many cases, like 90%, 95%, 99% intervals. And those intervals equal to, for example, mu plus minus z alpha over 2 times sigma over sigma x bar. Now you might be wondering what is z alpha over 2? We will see this later on, but this is usually a number that corresponds to a confidence interval, and the most commonly used number is 95%, and for the 95%, the z value here in that case will be 1.96. Now there's a formula behind this, but we don't need to know that. You just need to know those numbers. For 95% acceptance, the z value is 1.96. Now the second part of this chapter is about sampling distribution of the sample proportion. Again, we have some formulas here, but these are quite easy formulas. So P is the population proportion, and P hat is the sample proportion. The sample proportion equals number of items in the sample divided by the sample size. And we can also approximate that the proportion distribution using normal distribution. So it's quite easy. The expected value of the sample proportion is the same as the population proportion. Now the standard deviation of the sample proportion equals to the square root of P times 1 minus P over N. Again, there's an algebra behind this derivation, but we are skipping the algebra part for this course. You only need to know the formulas and how to apply those formulas. We use those formulas to standardize the p hats to a standard normal distribution. So it becomes p hat minus p over square root p times 1 minus p over n. And that means that kind of distribution, again, will be distributed like normally, with mean equals 0, variance equals 1. So if you can convert the question into such type of formula, then you can use the normal table. So here's an example. Here the proportion is 0.4 and we have a sample size of 200 and we want to know the probability that the proportion is between 0.4 and 0.45. Again, what we need to know is we need to convert this into a standard normal distribution. And here we do this. The mean is the same. The mean is 0.4, the mean proportion. And the standard deviation of the proportion, we use the formula to calculate here. And we put those numbers into the equation. And we find the probability of the standard normal distribution. And from there on, we can use the standard normal distribution table to find the probability. And for this one, the probability that Z is between 0 and 1.44 equals 0.4251. So we started with this question, the sample proportion probability to be between 0.4 and 0.45, and then we converted this into this problem. So that's actually something that we're going to do in all of our research. We will have a problem and we will try to convert it into some sort of a well-known distribution which we can calculate the probabilities. Now, if we are looking for the sampling distribution of a difference in sample means, then the formula here becomes a bit more complicated because now we have two distributions. We have x1 and x2. But still logic is somewhat the same. So on the right side you subtract the mean values, and here this is the standard deviation of the subtraction, and again you convert the problem into a standard normal distribution, and then you can use the formula. So I'll skip the activity and that's it. So far we learned about the standard normal distribution of the sampling mean and sample proportion, and this is how you calculate probabilities from the sample.